So this is the 11th lecture, I think, or 12th lecture, sorry. This is the 12th lecture of CEE, and we are studying linear state feedback. Let's review for a moment the problem. So suppose that you have a linear system described by a state realization, x dot equal to ax plus bu and y equal to cx. And you have access to the state. So initially, we are going not to consider this output equation. And you want to feedback the state. So the structure of your control law is a linear combination of the state variables, kx. K is a row vector, x is a column vector. So this is just k1, x1, k2, x2, and so on. And I've added here a term which is related to the reference. For the moment, assume that this extra term is just 0. And think of it just to have an idea of what an external term would enter. So the objective is that in open loop, your the poles of the system are just the eigenvalues of matrix A. So that's the determinant of Si minus A. I call this the polynomial A of S, small cap A of S. Okay, and I write it in this way. So Sn plus A1, Sn minus 1, etc. up to An. And I want to select the gains case such that in closed loop, the closed loop characteristic polynomial is an alpha of S that I specify. So for instance, if I know the desired closed loop poles, then I can build a polynomial which is this alpha of S. So in terms of a block diagram, we have our plant, which is this dotted rectangle, and inside you have the state model. I mean, I'm assuming that our plant is represented by a linear state model, and that you have access to the state x. So you multiply by k, and you feed it back. Okay. So remember that from an engineering point of view, the dotted rectangle represents the physical plant. So you have here some DA converter, here some AD converter, and the outside is nothing more than software in a computer, okay, that reads the data from the AD converter, which that is connected to the sensors that measure the state, and you do some computations, just a linear combination of this measurement, and you feed it back. And then you write it to the port related to the DA converter. Now, let's think in mathematical terms, in modeling terms. You have these two equations. One equation that defines the plant, and the other that defines the controller. So you can eliminate U, and if you eliminate U, you get a closed loop system whose dynamics is A minus BK. Okay, so you have changed this A minus BK. You have changed the dynamics depending on this vector K. And this external term R is just multiplied by B. So for the moment, R is assumed to be 0, so this is not much important. What is important is that when you select a value for the vector gain K, you are imposing the poles of the closed loop. And you want to adjust the poles of the closed loop such that these poles are the roots of polynomial alpha that you specified. So you want to solve this equation. So if ak of s is the characteristic polynomial of the closed loop, okay, and alpha of s is your specified characteristic polynomial, you want to solve this equation. And you solve this equation by equating the corresponding coefficients of these two polynomials. And you get a system of equations on the entries of k. So you get something like this. Okay. And I claim here that this system has a solution whenever the pair AB is controllable. Okay. This is something that we are going to show today. So this is something that we have seen in a previous lecture. Any question about it? One practical way to solve the problem for moderate or for very low order system, say second order or third order, no more than that, is to actually solve this by hand. So you have these equations and you solve them by hand. So this is the method of unknown multipliers. But then I said, okay, we have some formulas. One of them is the Bass-Gura formula that allow you to compute the vector of gains in a systematic way. And this formula looks a little bit cryptic. So you have alpha and A. Alpha and A are defined here. So they are made of the coefficients of polynomial alpha of S and A of S. And you have here the inverse transposed of this matrix, which is a lower triangular matrix. Observe that this matrix always has an inverse, because what is the determinant of M?
1.
1, that's right. It's a lower triangular matrix, so the determinant is just a product of the elements of the diagonal, okay? Because it would be 1 times the determinant of the first minor plus 0 times, okay, the determinant of the matrix that you obtained by deleting the first row in the second column. So this is 0 times something, it's 0, and so on, 0, 0, 0. So that's just 1 times this determinant. And you go on and go on and go on, and you see that the determinant of M is 1. This M matrix is always invertible. And pay attention also that you can invert and transpose and transpose and then invert, and the result is the same. So I just write minus transposed, okay? Because the order in which you transposed and you compute the inverse is immaterial. And then you have here this C minus 1, which is, and this C is the controllability matrix of the pair AB. Okay? So for this, if this formula is true, your controllability matrix must be invertible. Okay? And here, this formula is related to systems with just one input and one output. So you have a link here with controllability. If the system is controllable, if the pair AB is controllable, then the inverse of the controllability exists, controllability matrix exists, and you can compute the gains in this way. So now I would like to prove this formula. Okay, we have seen one example, how to use it, but let's prove it. And the first thing is to look for state realization. You know that a transfer function can have an infinite number of state realizations with the same transfer function. So find a state realization such that the gain computation, or the gain of the state feedback controller is trivial. So one suggestion is that we use the controller canonical form. So given, say, let's do an example with a third order system with 2 zeros. Given the transfer function, this block diagram realizes, okay, this transfer function. That is to say, if we compute the transfer function of this block diagram, you get the transfer function on the right. Okay. Now, let's suppose you have here the stage xc1, xc2, xc3. Okay. Now, let's do a feedback of this state xc. The C means that it's the state associated to the controller canonical form. Of course, you can write the state equations in this case. So if you write it, what you do? You do a feedback of xc1 by minus k1, feedback of xc2 by minus k2, and so on. Now, minus k1 is in parallel with minus a1. So you can lump everything together and say, well, this is the coefficient of the closed loop polynomial, because if I have not a feedback, if I don't have any feedback, a1, a2, and a3 are the coefficients of the denominator of the transfer function. So they are the characteristic polynomial of the system. Now, I'm just changing the value of a1. Instead of having a1, I have a1 plus k1. Okay? And if I want these values to have some assigned value alpha, alpha1, alpha2, alpha3, then I just have to solve the equation minus alpha1 equals to minus alpha1 minus k1, okay, in relation to k1. So in general, the vector of controller gains in the controller canonical form, so I put here the C to emphasize that, is just alpha minus a, where alpha and a are the vectors of these coefficients a1, a2, a3, and alpha1, alpha2, and alpha3. So you understand the argument up to now. The point is that if you are in this canonical form, designing a state feedback such that you have poles at the roots of a polynomial alpha, due to this structure, it's very simple. You just compute a vector of gains, which is the difference between the entries of the vectors of the coefficients of alpha and a. Any question? Now, you have one problem, which is your state realization in general, it's not the controller canonical form. So what shall we do? So you start with a state realization, which is generic, some A, B, and C. Okay, let's forget about the C. And you want to compute the gains for the state in this that correspond to this state realization. But this is difficult in general. Okay, so what you do a change of coordinates, x equal to t x of c, that lead you to the controller canonical form. Okay, in controller canonical form, it's very easy to design the controllers. So you get the gains in the controller for the state of the controller canonical form. But then you have to invert this transformation. Okay? Now, what is the transformation that leads you to the controller canonical form? Remember, we have seen that two controllable forms of the same order are related by a transfer function, which is the controllability matrix of X times the inverse of the controllability matrix in the other of the transformed state. Okay, and I told you in the last class that this is nothing more, this M transpose is nothing more than the controllability matrix of the controller canonical form. So the transform is just this. Okay, so what we have, I think that, okay, so you do this transform. Now you compute the gains, and the gains are Kc alpha minus A. And now you have to invert the transform. And for that, observe that you want to compute A equals to, there is a minus missing here, U equals to minus Kx. But X is Txc. So the controller, the gains in the controller canonical form are nothing more than minus Kt. Okay? So if you know Kc, you just multiply on the right by the inverse of T, and you get K. So let's put everything together. What do we have? I think I did some simplifications in these slides, but let's go to the Bass-Gura formula. You have alpha minus A are the gains in the controller canonical form. And then this is just the inverse of the transform that lead you to the gains in the X realization, state realization. Okay, so this formula is apparently very cumbersome, very strange, but actually it's very simple. You can get it using this very simple argument of starting with a state realization, doing a state transform such that the problem of pole placement becomes trivial, solving this trivial problem, and then inverting the transform. Any question about this proof? No questions? Okay. We have other formulas as well. One formula which is perhaps better known than Bass-Gura is Ackermann's formula. Okay, in Ackermann's formula, it has this structure. So this is a vector with zeros, and the last element is a 1. So this is nothing more than the last line of the inverse of the controllability matrix of AB. And then you have the desired characteristic polynomial computed for S equal to A. So you replace S by A. Okay. And Ackermann's formula is actually programmed in MATLAB. It's a function Acker. Okay. And you have another function which is place. Place is better. The numerics are better. So if you have multivariable problems, which is something that we're not going to consider, but anyway, and if you have plants with order bigger than 10, you should use place. So Acker works well for small problems, for problems of small dimension. Okay, so now we know how to design gains for, do the placement, to do pole placement. Okay, and I would like you to discuss with you this problem. So suppose that you buy a Fiat Punto, okay? And well, a Fiat Punto is a quite respectable car, but it's not so fast. So what you do, you go to the supermarket and you buy some electronic components, and you buy an Arduino, okay, and you do a state feedback so that you control the velocity of the punto. So you measure the velocity and the state of the velocity model, and you feed it back, okay? And then you say, well, my poles should be, what should they be? Very small or very big? If you want to have a very fast car, how should the poles be? Close to the origin or away from the origin?
Away.
Away. Huh? The farther away, the fastest the model, the car will be responding. So you want to, the punto goes to 0 kilometers per hour to 100 kilometers per hour, I don't know, 12 seconds or 13 seconds, I don't know. And the Ferrari goes, changes the velocity between 0 and 100 in 3 seconds. So 4 times faster. So you want to have, to change the poles so that your punto becomes a Ferrari, at least in the acceleration. Do you think this is possible? Let's look at the Bass-Gura formula. Let me place the Bass-Gura formula here. What does your intuition tell you?
That no, it's not possible.
Probably it's not possible. Otherwise, people were buying puntos, painting them in red, and okay, it's not possible. Why is it not possible?
Because the hardware is a limitation.
The hardware is a limitation. And in terms of feedback control, this means what? You can speak in Portuguese if you want, and I will translate. So you have your velocity set point, say 100 kilometers per hour. The car is still, is stopped, no? Is standing still, and your set point is 100 kilometers, and you want to go there as fast as you can. So what do you do? What are, in terms of feedback, what do you do to make a faster car? What do you do in a feedback controller to have a fast response?
You make the poles bigger.
Yes, and how do you select the poles bigger? I mean, think about the basic things that you have learned in, what do you change? You don't change directly the poles, you change what?
The gain.
The gain. So you need what? What type of gains?
Very big gains.
Very big ones. Now, so and if you have very big gains, what happens?
If the system can keep up, it becomes faster.
Yes, but then there is a limitation of the motor, and
then it won't follow the model.
Sorry?
And then it won't follow the model.
Why not?
Because it can't keep up.
There is a saturation, okay?
Yes, yes.
There is a saturation. So there is a maximum that you cannot go afterwards. So you are clipping what happens. Suppose that you do just an output feedback, okay? So you compare the velocity and you have a big error with a big gain. You have a big excitation to the motor. The excitation would mean that you are injecting a lot of fuel, but the fuel that you can inject has a maximum value. Okay? So due to this saturation, it's not possible. Now let's think about feedback, think about state feedback, okay? Where do you see this effect of relating the fact that you make the system very fast and the gains become very big? Where can you see this in Bass-Gura formula? You remember the meaning of the symbols? So alpha is a vector of the coefficients of the desired polynomial. A is the vector of coefficients of the open loop polynomial. M is this matrix that depends on the open loop polynomial, and C is the controllability matrix. So where is something that tells you that when you make the closed loop system very fast, K grows a lot? No ideas? You have this alpha minus A, okay? When you change A, remember, define the open loop poles. So it's a polynomial that defines the open loop poles, and alpha, the desired closed loop poles. So if you make this very different, alpha minus A will be very big, and K will grow, will be also very big. So if your closed loop poles will be much faster than the open loop ones, then the gains will be very big. Do you understand this? Is this clear? Do you want to make questions? Yes, questions. You want to make questions?
No, I was saying that it was made clear.
Okay, okay. Now, let me ask you, why do you do feedback? Reasons for doing feedback.
To control the system.
Sorry, I could not understand you.
To control the system.
To control the system, but okay. What do you mean by that?
So we can follow a reference. If we don't have feedback and
okay, so to automatically follow a reference. Okay, that's one good reason. And if you want to follow a reference, then there are some, let's say, sub reasons for that.
We need to watch the output to handle the input in a certain way.
Okay, that's making things automatic, no? Making things automatic. But for instance, if you have a table, you can say, well, I have a table relating the input and the output. So I use the inverse of the table, the static gain. So I have a system with a static gain of 5. So I use a controller, which is just a gain of 0.2. So I apply my reference through this gain, and in the end, in steady state, I have my output following the reference. Does this always works? There are reasons why it should not work. If you have disturbances, that's one reason. Feedback attenuates the disturbance, the effect of the disturbance. Also, you can have an open loop unstable system. And if you have an open loop unstable system, you would never reach steady state. So you want to place the poles of the closed loop such that the control system is stable. Okay? And you have important classes of systems that are open loop unstable. For instance, the space shuttle in landing. Space shuttle no longer exists, but it's a very, or military aircrafts that are unstable at low velocities. When they land or when they take off, they need a controller to stabilize them so that the pilot is not controlling something which is unstable, or certain chemical reactors that liberate energy. You have various equilibrium points, and around some of these equilibrium points, the system becomes in an open loop unstable mode. So you want to stabilize it, and that is to say, you want to position the poles in the left half plane. So stability, stabilizing the system, or making the system a little bit faster. But as you see, there is a limitation when you want to make a system a little bit faster, because you have now saturation of your actuator. Okay, because the gains will grow. The faster you make the system, the bigger the gains are. So you have to watch for the limits of your actuators. Okay. Any question or comment about this? So I would like now to discuss with you something which is where can I place the poles? So what is your suggestion to place the poles? Remember that the polynomial alpha is made by terms which is s minus each of the poles that you want to, each of the value of the poles that you want to specify. So suppose that you want to control a system, and you have to select the poles. Actually, this you see that the formula of Bass-Gura computing the gains is something that MATLAB does for you. So the engineer work is to select these poles. So where should you place the poles? Give me rules to select the poles, the closed loop poles.
If we want the system to be fast, we need the closest pole to the origin to be the furthest away possible, for example.
I could not understand. Can you repeat it, your sentence?
If we want the system to be faster, we need the closest pole to the origin to be the furthest away possible.
Okay, so you want to make the system a little bit faster, but as we have discussed, there are limitations. No, there are limitations. There is one basic rule about the position of the poles. If you think of big regions, left or right, this can have also a political connotation. Where should the poles be?
On the left-hand side.
On the left.
Plane.
Why? Why on the left?
Because if they're on the right, we know that the system will be unstable.
Okay, so you want to have a stable closed loop. That's basic. So all the poles should be on the right half plane. But now there is a lot of latitude for that. Maybe you can do some simulations. For instance, so let me give you one example. It's a military one, and hopefully we won't use it for military purposes, but it's something that it's a good example, so I will use it. Suppose that you have an armed car, okay, a tank, a cannon tank, and you want to turn the tower of the tank. You have your cannon, and you want to point it at the target. So you want to regulate the direction to which the tank is pointing to. Now, suppose that your cannon is initially pointing in the direction which is opposite to your target. So you want to make a very fast movement of about 180 degrees, and this must be very fast. So what is really important is that it is fast. It does not matter that it has some overshoot. What is important is that very quickly you change your cannon to the direction, to the correct direction. Okay. Now, suppose that you enter a situation in which your cannon is more or less in the direction of the target. Then the overshoot is quite important. So you switch to another controller in which you don't have any overshoot, and the precision is quite important because now you are pointing at the target. You see, you have this type of movements. So sometimes you want to take the state of your system out of some position. Okay? So probably you will accept some overshoot in the final response. And in some other cases, you want to have to do fine tuning. So you want to have your state moving around the final value. Okay. And there are tables actually, probably you solved some problems based on characteristics of second order systems or third order systems or second order systems with zeros and so on. So this is a classical thing studied in the basic course on control. But to select the poles or to select the gains, implicitly when you select the poles, you select the gains, and when you impose some gains, there are some poles associated to them. You can formulate this in an optimal way. Okay, the optimal way does not mean that it is a good way, but it's according to some definite criteria. And this criteria is this. Suppose that you have your plant x naught equal to ax plus bu. So you select your u such that this integral between 0 and infinity, and you see that you have a quadratic form in x and a quadratic form in u. Okay, actually it's u squared. Suppose that this matrix QR is just the identity. So you have here the sum of the squares of the components of x. Okay, this means that if you select your controller to minimize this term, x transpose QRX, then you want your state to have a small value. Okay, that means suppose that you have taken your x away from 0 due to some disturbance, and you want to drive it again to 0. Okay, 0 is the equilibrium point, and you select your controller such as to minimize the integral of the sum of the squares of x is nothing more than the energy that you spend with these terms that you are that is associated with these entries of x. Okay. Now, if QR is not an identity, maybe you are giving more importance to some entries of x than to others. For instance, if x is made of a position and the velocity, you can say, well, the position is more important for me than the velocity. Okay, so you put the coefficient of q. If it is a diagonal matrix, you put the coefficient of q corresponding to the position at a higher value than the one for the velocity, because then it is more important. has more weight here. Now you have also this term, a coefficient r times u squared. Okay, u squared is the power. So if you integrate it, it's the energy. This corresponds to the energy spent in the control. Okay, and there is a kind of waterbed effect. So if you say, I want the energy in u to be small, then you are letting your x to be free and changes more. But if you want to if this power is, if this coefficient is big, okay, then u is small because you are minimizing it, and x will be free. Okay, so small u means that you are giving freedom to your x to go away. But if this coefficient is small, then spending very high values of u is not much important. So you are allowing u to change a lot, and this will change in a way such as to keep x small. So u small means x big, and u big means x small. You see, there is a trade-off between these two terms. Okay, and you can control this trade-off by adjusting RR, and this Q matrix is allowed to tell you what variables in X are most important. Now, how can we design a controller such as to minimize this quantity? Okay. We are going later to see the solution. Actually, proving these formulas will be part of the last part of the course, but let me give you right away the solution. So the solution is a state feedback. Look at the bottom of the slide. So the solution is minus some gain kx. So it's a state feedback, exactly as what we have been studying. And this k is computed according to this formula. So B comes from the model of the plant. It's this B matrix. R, index R, is the weight on the control variable, and it's inverse. So this weight cannot be 0 because otherwise you have here an infinite number. Okay, so you need some regularization on U. And then you have this P. This P is a matrix. Okay, this P is a matrix. And probably there is a transpose missing here, I think, because this is B transpose P, sorry, I'm sure, because K is a row vector, P is a matrix, and you multiply on the left by a row matrix. B is a column vector, so B transposed is a row vector, so this is B transposed. And P satisfies this equation. Here, you see, it's an algebraic equation. The thing new is that it's a matrix algebraic equation. It's called the algebraic Riccati equation, or ARE, equation algébrica de Riccati. Okay, and you see here that you have some linear terms. You have here a quadratic term because P multiplies P in this term here. Q is that matrix. So the game here is that you select R and Q and you solve this equation, the algebraic Riccati equation. And then you compute K using the solution of the algebraic Riccati equation, and your control law is the last one. Okay. Now, to solve this quadratic equation, you need to use some numerical method. And I'm not going to worry about it. You can use it, you can compute it with a LQR function in MATLAB. Okay, LQR, why? Because this is the linear quadratic regulator. Regulator, you are regulating your x to 0. This is a regulation law, no reference. The model is linear and the cost is quadratic. That's why this is the LQR problem. Okay. So this is a systematic way of computing the gains. And now, let me give you one example. Let me give you one example. Suppose that I have this state system, this state model, okay? That corresponds to the same matrix and to this B vector. And you do a state feedback. So this is the state, the block diagram. So you do a state feedback. So your U is minus K1x1 plus K2x2. And you want to design K1 and K2 using this technique. Now, you apply those formulas and let's see what happens. Let's see what happens. So you have two components of X, and you also have U, okay? And in this case, you see that I'm giving more importance. I'm giving more importance to the first component than to the second component because I'm weighting x1 by 10, the power of x1 by 10. So when I have this term here, this will be x1 squared times 10 plus x2 squared times 0.1. So I'm giving 0.1. So I'm giving I'm attributing more importance to the first component and to the second one. And the first component is in blue, and you see that the second component has this behavior. Now, if I give more importance to the second component, you see, compare these two graphics, okay? The second component, the green one, goes to 0 much faster than before. Okay. Now, what is important here is a relative idea. So you can say, well, what is more important for me? It's one variable or another variable. Of course, you can also use non-diagonal matrices, but in those cases, you will lose your intuition. Now, suppose that I keep the Q matrix constant and I change the R matrix. Okay, so here the R matrix is 1 and here the R matrix is 0.1. So when I reduce the R matrix, what happens is that I allow the U to be much bigger. And look at the beginning. When I have an R matrix, in this case, this is a scalar of 1. The biggest value is biggest in amplitude, so in absolute value, is in the beginning, so minus 1.9 or something like that. But when I reduce the R parameter, then it becomes bigger, it becomes minus 5. So you more than double the amplitude. Okay, so you can adjust this weight to shape the amplitude of U. Now, what happens? Look now at the state. When you have decreased R, So your control action is much more aggressive, and you are able to drive the state close to zero much faster. Okay, here you are at 0 before 3, and here you are at 0 around 5. You see? So on the left, with a bigger value for R, the system is much slower than on the right. Actually, you can compute exactly the closed loop poles in both cases. We will study that later. But playing with R, with this matrix R, allow you to control how aggressive is your controller. So if you have some saturation limit, you increase R so that you don't reach that saturation. And at the same time, it makes the system faster when you decrease it. Okay? Now, usually you say, you think that getting a fast response is something that is a good thing. But don't forget that your system is not exactly equal to your model. So you can have high frequency dynamics. When you start making your system too fast, what happens is that you start exciting this model dynamics, and you can destabilize your system. So perhaps you would like to increase R a little bit so that your system becomes slower, the bandwidth becomes smaller, okay? And you don't excite the high frequency dynamics because the gain of the closed loop has decreased so much in high frequencies that this high frequency parasitic or a model dynamics is no longer excited in a way that it causes instability. Okay, so this method, this LQR method of design, is a systematic way of designing the feedback controller gains. You can compute the closed loop gains by just computing the determinant of SI minus BK. And how can we design the Q and the R matrices? The Q, if you select it to be diagonal, allow you to give more importance to some values of the states than others. And R allow you to make the system more or less aggressive. This means that you can compute, you can also influence the speed of response of the system. And sometimes you don't want the speed of response to be too fast because of a model dynamics. Okay, questions about this issue? In your lab work, I'm giving you the A and B, and you have a regulation problem. So the pendulum is not exactly equilibrated, and you want to drive it to the equilibrium. Okay, equilibrium means x equal to 0 because x is the corresponds to the increments with respect to the equilibrium point. And knowing A and B, you can apply this technique to find K, okay, and to design a state feedback. And you will have the opportunity to see these things because maybe this year you want to work with a true system. I don't know. This is still something that we should decide. But if you work with a true system, there are many parts that are very fast, but they are not modeled. Okay, so the model that you are based on is an approximate model. So playing with these matrices is an important way of stabilizing your system. Any question? or comment or doubt or? There is one thing here. If you think about your laboratory work in which you have to you want to equilibrate the pendulum, there is one thing missing here. Do you know what it is? I'm assuming that I have access to X. And in the pendulum, I just measure the position. And actually, the state of the pendulum is 4 or 5, can't remember. Because you have the position and the velocity, and then you have an arm that moves to equilibrate the pendulum, a rotating arm with a motor that gives you 2 more states. So at least you have 4, dimension 4. And I'm just measuring one variable, okay? Which is the angle of the vertical pendulum. So I need a way to estimate the state. So the things that we are going to study next, and we will do that on Wednesday, is how to replace this control law by another control law in which instead of feeding back the state, you feed back an estimate of the state. So this implies how to build this estimate, and also what are the implications in terms of the design. Okay? But that is something that we are going to study next Wednesday. Any question, any final question?